Archiving started.
Okay, everyone, can I have your attention? I would like to introduce our speaker today. This is Michael McCullar. This is actually his second talk that he's given for the lecture series. The first one, it was a few years ago, and he was talking about this satellite, this telescope at the time then. Right. And so at the time, what happened was it was sort of a last-minute thing, and he was actually the second of two speakers. And so today he gets the spotlight to himself. So with that, I'll turn it over to the speaker. I think this is something you guys will find very interesting, and that's it.
All right, thank you. Okay, as Dr. Garrison said, my name is Michael McCullar, and we've been working on an interesting project for a number of years now. It's a interferometric telescope system. So an observatory system that uses multiple telescopes, individual telescopes, in an array that functions as one large telescope. And so we've named it Macho Mengi, it's Swahili for many eyes, or otherwise M2. We've had a number of partners over the years. You can see on the side. This project is headed up by the National Society of Black Engineers, but we have a number of university partners, corporate sponsors, as well as nonprofits. So Macho Mengi, it means many eyes in Swahili. It's an observatory system. It involves numerous ground-based and space telescopes that will actually function together to act as one large observatory. Okay. What I'm going to do is give an overview, the full vision of what we were trying to accomplish. On this development plan that you see here, it just recaps kind of what the different steps, which I'll go in more detail on. We'll start with the research test bed, some of which has already been developed by Texas A&M. There's other research that we've already have done. For instance, collapsible space telescope. We had a project with NASA Ames a few years ago to do a feasibility study for a CubeSat-sized space telescope. And then NESBYSat-1 was our single telescope for NESB, the ground station, and then the NESBYSat-2, which would have been the Constellation of space telescopes. But there are numerous partners, so NESBYSat will not be the only one. The key collaborators, see here myself, Dr. Howard's our chapter president. He works at NASA. Dr. Dave Hyland, he is a professor at Texas A&M University. He's the one that we're going to as our principal expert on intensity correlation imaging, which is a technique that we'll use to combine the imaging of the telescope. Dr. Daniele Mortari, he's principal expert of flower constellations. I'll go over that later, but that is a form that allows various objects, lack of a better word, satellites, to stay in formation without the use of robotics. And a few of the other key partners that have worked with us. You see the names there. What this is really, we're heading this up as an educational program. So in NESB, which is heading up the program, we had 4 key areas that we wanted to introduce to schools, universities, as well as grade schools: rocketry, CubeSats, robotics, M2. All of that is kind of combined into human robotic spatial exploration. So we have a lot of different projects that we're working on, but I will talk more about the M2 project on this presentation. So from an educational perspective, we want this project to be a real hands-on project for the students. So while students are following the project from high school through the college level, I myself have since graduated, so the professionals are involved too. We want this to be a hands-on learning experience, and so the focus is not necessarily on the components, but having students think of systems, the entire systems perspective. So you have your various concentrations that you're in, your various disciplines, but when in say the real world, I always say, but in developing hardware or even software, you've got to think in a systems perspective, how your component fits in, with the grand scheme of things, and then how that system flows from end to end, from the actual sensor per se, or the hardware end, all the way down to the user end. So we want students to gain that kind of perspective, and we'll be introducing them to systemic thinking of things in an integrated fashion. And so this kind of bypasses the old way of learning by regurgitation. What's the formula of this? What's the formula of that? And just spitting out information. We want students to be able to think, because that's how the real world is, or your own home project that you might be working on. You have to think problems through. There's no answer in the back of the book. So there's various techniques that we are introducing to the students. One is intelligent fast failure. It was introduced to me by one of the names on that list, Tony Bruin, also works at NASA. The students that he teaches, a lot of them are very good students, but have never experienced failure, or very few times they've experienced failure. And so when they get onto an actual project on the job where there is no answer, there is no defined way of doing it, and they see failure for the first time, sometimes it shocks them. So he says that failure is part of the process. NASA has a logo has the term failure is not an option, but that's an operation. While you're in testing and development, failure is the way. You need to fail, and fail as fast, as many times as possible, to learn how your system is going to function. Put it through the rigors so that when you finally got through the operation side, then there's failure is no option. So we want to introduce students to that concept, to where outside of the normal project where you have to solve so many problems and there's an actual answer, we want to introduce this to them while they're working with us in this project. Some of the tools that we came up with along the way, when, about 2 years ago, when we started learning on our own about interferometry, how to combine the different telescopes, we were short of cash. Optics takes a lot of money for optical equipment. So we said, okay, how do we keep the project going? We don't want to be delayed just because of funds. That's something we're always going to have to deal with. We looked online, and a couple of universities had used Legos for optics. It's a grid system, lines up everything perfectly. I said, hey, that's a great idea. Let's try it. Let's do it. Let's learn about it. It's Legos, yeah, but it worked. Now, the mirrors we had weren't the greatest mirrors. That does matter, but the actual system works. So the tool that we use to learn from, we developed a simple interferometer. The diagram off to your left is a microscope interferometer. It takes a light source, splits it, hits off the two. I don't have a laser pointer, but the M1 and M2 are mirrors. There's a pointer. Okay. M1 and M2 are mirrors. This is your light source. The light hits the beam splitter, reflects, bounces back, and recombines. And the image that you see here is a fringe pattern. That's what happens when the light, when your light waves are combined, or it forms a pattern. And that's how you know that you're basically aligning the light waves up, which is what interferometry is all about. What this is a simple model demonstration of, instead of M1 and M2 as a mirror, imagine those as telescopes. And so the same thing happens. You get a starlight will hit the two telescopes, and through a series of mirrors, it recombines the light, and you form a fringe pattern. They go through. They take this pattern, goes through imaging software, and that recreates an actual image. And so now you have a telescope working off of two separate systems. The power of the system is not dictated by the size of the mirror, but the distance between them. And so instead of say a 6-inch telescope that's separated by 6 feet, you might have a 6 feet, simulating a 6 foot large diameter telescope. So this is the first introduction into interferometry, and as well as optics. And so we're taking this tool, we're kind of redesigning it, and we're going to introduce this to the high school so that allows them to get on board with the project. Well, I said before, teaching STEM is how to apply your fundamental academic into real world systems. So, and I'll go into more, this is more on the lines of the organization and how we're incorporating the schools. So we said, hey, high school students, students in general outside of the industry, they're still learning, but they don't know what's impossible, what's not possible. So let's bring them in. Let's take that mindset, bring in your high school students, have them innovate. So I said the light bulb, one style of light bulb. Bring your college students, have them also innovate. They have another type of idea. Now mix the teams, and you have a new type of idea from that mixture. So, like I said, we're going to be engaging the high schools as well as the colleges for the same program. And for the high school students, this is going to prepare them for college. I named a few universities in the Texas area, as well as the college students, helps them prepare for to be employees in various companies. We're also looking for NASA partnership in this, something we're still working on. But the idea, again, is to introduce students to work side by side with mentors, something we've talked to a number of NASA people about. That's still in work. But we want to bring in a number of avenues, academic, government, nonprofit, so on and so forth. Okay, a little bit of background, just more background about what our NSBE has done and some of the platforms we're intending on using. This is a project we did at NASA Ames. It was a feasibility study they wanted to know if it was possible to make a space telescope the size of a CubeSat. So this is a 6U unit. 1U is 10 by 10 centimeters and area, 10 by 10 by 10 volume. This is a 6U, 6 times that. NASA Ames had an existing bus here, your avionic navigation controls, all packaged here, your solar panels provide power. So they had a packaged unit. We developed the hardware, so we developed we designed preliminary design of a telescope that would fold down into the volume, and then when it's deployed into space, it would extend to its full focal length. So there's a secondary mirror. The primary mirror sits down below where the camera is also, and that integrates into the system, their existing system. So we wrote a paper up. We had students involved, and we're intending on using these types of satellites, maybe not this particular one, but these types of satellites for our space system. Okay, so now what will M2 do? As I said, this is the grand vision. So what you have here, remember our CubeSat, we start with a ground system, various telescopes, and it does not really matter the size of them. They could be amateur size up to observatory, professional observatory size type of telescopes on the ground, stationed in various areas, as well as space systems. All of their data centralized and where the storage will be, where the user interface will also be. What this is showing here is the possibility of what we'll do is, from what Dr. Highland was saying, the technology, the hardware technology right now, if we had the money and the time to develop everything right now, we would be able to take images of the surface of a star. So if other stars had sunspots, like our sun does, we would see it. I don't think that's been done yet. But that's the level of technology that we have, that we're working on. And if it was fully built right now, he said, that's what the capability we have, capability would be. We actually want to look at exoplanets, take a higher degree of technology, finer sensors. He found one that could possibly do that. But right now we're saying, with the technology available today, and we would build this system, this is what it could do. In addition to that, same hardware, no change in the hardware, but change in technique. you can also detect asteroids. So near-Earth asteroid detection. What this is symbolizing is that he's called it stellar occultation. When an asteroid is moving, it's not actually looking at the asteroid, it's looking at the stars winking out. So as the asteroid is passing in front of the star, it goes out. And as it slowly moves through the sky, you'll see this shadow moving. And so this data is recorded over long periods of time. This could be hours, this could be days or weeks. But the software would say, hey, we saw a shadow here yesterday, today it's over here, and then it's continually moving. There's something out there. So this is he gave me a resolution of this. I think he said that I think maybe about 2 years ago, the asteroid, the meteor that hit over Russia, he's more of an expert on this. He said it was probably about the size of a refrigerator. That's not a damage it did. And it's only the size of a refrigerator. We could not detect that. What his was able to do, he said, I think it's the size either of a house or a bus or so. With this technique would find. The refrigerator size, even still, as dangerous that is, even that is not detectable from our current methods. But this is magnitudes better than what we do have using this technology. And like I said, it's using the same hardware. The grand vision, have our space system, not just hovering over Earth. That's an early phase, but we want to go beyond that because the further you spread these systems out, the more powerful, the better the resolution is. The more you have, the clearer the pictures become. So in space, we say, okay, how do you get this information? This is an example of Flower Constellation. I'll show you a clip in a second if I can get to it. This is a representation of different telescopes or satellites. And I'll show, if I can get to the video, let's do it. Yeah. The intro. If you can imagine a juggler juggling balls in the air, from a distance, if you had enough of them and he's juggling fast enough, it would look like he's holding a shape. But each of the balls that he's juggling has no idea of the presence of the other one. And so Flower Constellation, the best I can describe it, is a sophisticated form of juggling. He's timing them so that each one of these is in their own individual orbit. They're not aware of the other. But timed right, you can keep a rigid formation. And this is just one example. He had some very wild other examples out there, but no robotics. Nothing is pinging off the other to track the other's movement and to stay in formation. If one fell off the sky, the other had no idea. It would stay in formation. Okay, so does it work? This is Texas A&M system. They built this already 2010, 2009 time frame. This telescope is about a 16-inch telescope. They were awarded about, I think it was around the lines of 140-something thousand. So each unit here is worth about $75,000 total. So what you see is a 16-inch telescope. First telescope is in a shed, stationary position. Second is in a trailer. Same type of telescope, same platform, almost identical in equipment-wise, but it's in a trailer. So if you see the diagram here, the stationary unit is somewhere in the center. It might not be exactly in the center, but the trailer will move. They'll take an image, always in pairs because it's interferometry. So they'll take a picture in pairs, move the trailer, another picture. Move the trailer, another picture. So, like I said, the distance between them, 16 inches here, but you're measuring this. That's what's called synthetic aperture, which is basically the aperture is the diameter of the telescope. you're synthesizing a much larger telescope. And so using this identical system, this same system, they were able to get a picture of a GPS satellite. GPS satellites are about 1,000 miles from the ground. The picture was kind of grainy. He did show us a picture. It was kind of grainy because they're only using two. The more you have, the clearer it will be. But individually, it would not be able to see that. But together, using this technique, they were able to get an actual picture of a GPS satellite sitting above Texas. So the plan is to simplify this because at the time they weren't sure what they needed. They had I'll show you this. One of the key components is the sensor. This basically measures basically it's a photon counter. It's counting photons hitting the sensor. It's not taking an image. It's just counting photons. So they have computer systems here. One is used to line the telescope up. One is taking the data. And if you can kind of see here, this is without it looking at anything, just noise in the background. And he pointed it at I forgot what it was, Jupiter or a star. I forgot. We were looking at stuff with one of them that night. This is what it looks like when it's seeing a star or a planet. It's taking this information, this intensity information, from both telescopes, taking the software and combining it, and then going through imaging software to produce an image. And so they've developed this. They have actually two of these. One's one of these is in Texas, on Texas A&M campus, and I had a chance to use it. We actually didn't get the interferometer working that night. They had just got it back online, but he did allow me to see how everything operated. But this particular picture was this past summer. And if you have any questions, go ahead and stop me, because this is the system diagram. So each telescope, he considered a light bucket. And what he's saying, the difference between this type of interferometry and amplitude interferometry is actually used, it's still a very niche area within astronomy, but there's a number of systems that use it. One, the largest is called the VLTI, stands for Very Large Telescope Interferometer, owned by the Europeans, and I think that's in South America somewhere. It takes 4 large observatories and several small telescopes and combines it. And they actually combine the actual light. So the light from each telescope has to hit a sensor at the same time, so that it's very complicated, but it actually works. They can get images better than the Hubble as far as resolution. Hubble probably has a clearer image, and they can't see as well, but because it's in space or out of the cloud, it can see clear. Yeah, it has a better clarity. Resolution is basically if you look at, say for instance, if I separated my 2 fingers, far enough back, it would look like I have 1 finger. You can't tell the difference between my thumb and my index finger. Closer you get, that's the measure of resolution. The way you can tell the distinguish between 2 different objects at a certain distance. That's the resolution. Clarity is more how clear is it. So, for instance, somebody who has a great resolution might see a fly on my shoulder as a dot, but clarity, you'll see me clearly, but you can't see the fly because the resolution is not there. So there's a little bit of difference, but what we're looking at is resolution. With this system here, intensity correlation imaging is a little bit different. It's taking the data. So we're not restricted to actually aligning the light. We can take data, save it, combine it later, just like radio astronomy does. Radio interferometry, radio telescopes, they do the same method. The telescopes do not have to be image producing. So he said as long as there is just a reflective material there, enough to get the light into it, the sensor, that's all that matters. So this could work in more cloudy conditions, not full cloud coverage, but a more some haze, can work in the daytime and still see stars because starlight is still hitting us through the daylight hours. It's just the background light interferes from our eyes. This will still pick it up. This is a sensor. That like I said, this is a basic count of photons, data card, and then your programming code where it continues on. At the time, they did not have a means to transfer data. So while they were out there a few years ago in the summer, they'd fill up a hard drive, pick it up the telescope system, run it over to the building, download it, come back, put it in. You know, so hey, $75,000 a piece. Hey, they got all of this, but they just said, hey, we know in networking it can work. This is about as far as we can go. At this point in time, we want to make advances in the networking because the greater the distance is, we're going to start with the ground, then we're going to go in space. How you get the data is going to be a big deal. Next phase is something that we've added. We want to display the information in a more interactive way. So how about 3D? What does a planet look like in 3D? How about touching it? So put a haptic device on so you can feel the planet. And so now you're engaging students not by just looking on a screen or in a book about what a certain planet or a star will look like. We want them to be able to hold it, move it around to at least, and with live data. They might not be able to see all of it because we're going to use live actual data, but what can they do with that? Now, and we started going off, hey, if they're holding the data, what about a blind man astronomer, or what about a blind astronomer? So now you're not limited by sight. You can feel the planet. You can translate the imaging data to sensory, your other senses, engage your other senses, and see and touch. So we're trying to get a new educational experience out of this. So the breakdown and the partnerships that we have, this is where your systems engineering comes in. We're designing this as a full system, end to end. So your telescope ends, nanosatellites, ground telescopes, all the way down to your user interface. Each part of that subsystem, every major subsystem, we've broken down, and this could change. We've had partners, so if they doesn't have a yellow dot, those are actual partners. Yellow dots are area people that we're still trying to get. But each partner will concentrate in that subsystem. We hope to get universities filled up in each of these blocks so that university is working on, say, the nanosatellite. Another is working on the control center, and maybe somebody on the computational side. Those students need to know how their component fits with the rest of it. Systems engineering. So from the very start, we're introducing this to students, as well as our business model of actually building this. So it might be hard to see. Phases. These are phases of development. We're currently in about phase 1 or 2. Phase 1 was our learning phase. The very first part of that was the Lego setup. But we're trying to learn ourselves. A lot of us are professionals that are actually in optics. We're in other fields. Myself, this is not what I do every day. So we're learning different things. So we're trying to get everyone on the same page. So we had an initial learning phase. Step 2, building an imaging interferometer. Texas A&M, I'll show you Texas A&M system. What we want to do is use their system, operate it, get an understanding of it, and then in our lab, we have an actual laboratory. We want to take their system as a tabletop system. So what they have, we want to put it on a table, lay it out, end to end on the table, a much smaller version, but we want to compare that with other techniques, such as amplitude interferometry or single telescope. We want to see what the differences is, get hands-on experience, what the differences are, how each one performs, what kind of image quality that we'll get from each one. That's phase 2. As well as start to get into the cube setup. Like a couple universities are already developing CubeSat platforms. Phase 3, Constellation test bed, we have the end-to-end system laid out. Now we start working the intelligent fast failure in there. And part of that technique is not designing in a linear fashion where you design a component, see if it works right, and hopefully by the time you get everything to work and you tell everyone, hey, it's ready. That's a linear fashion, because if something goes wrong, you have investors, you have people who are giving you grant money. You're telling them it's ready, but there might be a single component that doesn't work well with the others. And so we want to do, hey, side by side, put your different versions, version A, version B, version C, develop those side by side. Now play with it. Now make it fail, each side by side. And as you're in the development phase, you're testing multiple versions all together, integrating them, taking one part and putting in the other, doing all this up front. That's phase 3. By the time we get down to phase 4 and 5, we hope to move out of the laboratory into outside area, and that will be our first ground-based system. So when we move outside, we intend this to be a usable system, but still a test system. But in its mature stage, hey, we might have one here on this campus, put another at a high school, put another at our lab, and maybe another on top of Lockheed's building, okay? Still in the test mode, but now we're testing on the ground real time. While we're testing on the ground, these same ground systems are simulating the space system, because ideally, what we've been testing in the lab, we take directly in space because we've beat it up down here. By the time we're saying, hey, let's make a space telescope out of it, we've already beat it up. We're ready for that phase. We're not going to wait until the ground system's done, then test space, test it together, fail them together, because it's going to space eventually. So by the time we're in phase number 6, where nano-satellite construction and testing, you're basically now just certifying the satellite hardware. Phase 7 and 8, the launching nano-satellites, going into operation. And this system is expandable, so it may start off with 3 or 4, okay, and maybe 2 or 3 up in space, but it's expandable. So as more sponsors come in, the larger the systems will get. And this was just brainstorming on different funding avenues, from everywhere from direct sponsorship from corporations to crowdfunding. We had a celebrity sponsor back in January, Miss Debbie Allen. She was going to help gather celebrity support. So we were just brainstorming on various means of funding it and keeping it going. One of the good things about it, of going to the various universities for the various subsystems, is that the university, if their focus is on optics, they're already getting their funding for that optics, not for all Macho Mengi. So if it ever dies, unfortunately, the whole project isn't jeopardized. There's a number of people working on different things. So, but we've gained the benefit of their research. So we have multiple heads on this, so let's say this project can keep going. Finally, commercialization. We looked into various types of industries that maybe have need of distributed systems. Labs is interested in us because we're working on complex multi-satellite systems. They're more into the defense industry. This is more for astronomy, but a lot of people have their own needs out of this system, so they became partners. So there's commercial aspects as well with this. I did have a demo. Fortunately, my partner in crime isn't here. I would have showed just some examples of 3D imaging, but we'll still, maybe the next time we'll have a full demonstration of the 3D imaging where we'll take actual images, convert them in 3D, and we don't have the haptic device yet either, but we'll show that, just to give you an example of how this actually could feasibly work. And that's pretty much it. I think
yeah, thank you.
Were there any questions?
Yeah, I have a question. Okay, so when you have all these different CubeSats in orbit, and if you want to change what you're looking at, I mean, how do you steer them so that you're looking at a particular object or star? I mean, you have to, coordinate all of them to turn, or is that design in the orbital mechanics of it, or what?
I think the short answer is yes. It would depend on the individual design. So if we go back, each of the telescopes will have to arrange itself at that object. And so depending on how far it is, some will be pointing this way, some will point this way, but they'll have their individual control. And then also the way they're arranged. Of course, on the ground, there's only one plane, but it would all depend on what we're looking at. But we're anticipating that kind of challenge. It's how to point them all, how to keep them all, especially the space units, how to keep it steady for X amount of time. So that's part of the research that we're trying to find out.
I have two quick questions. Question number one is the Flower constellation. That's a very interesting process. But I was curious, so if they're going in a formation, but they're not communicating with one another, have y'all planned out a possible way to repair one if it does get lost, so you can maintain your distributed system?
No, but I mean, that would be an interesting thing to find out.
Repair or replace it?
Yeah, repair or replace. Yeah, it is something that we'll have to also answer. I mean, we're still in early phases, but that is something that we would be interested in people who have ideas on that. Because obviously it's going to expand, and some of them are going to fall out, fall out the sky if they're in a low orbit. So we will want to know how to do that.
My other question was, since you're not packing in the hardware needed for the sort of combined telemetry, does that mean that you're using that space to make it more compact, or does it mean that you're using that space to increase the observational capability?
On the CubeSat one? Okay, let me go back to everybody sees what we're talking about. So you're talking about when it's compressed like this and then it expands?
Yeah, the fact that they're not communicating with one another, that's not hardware, obviously, that
Yeah.
you don't have in there. So having saved that space because you don't have it in there, is that more so that you get that impact size, or is that more so you can add additional hardware to the observation?
Well, and I hope I'm answering it right. The compactness of this system is just so we can fit it within the box, because there's a deployment mechanism that's not shown here that we have to deploy out of. What we hope to have is a powerful enough transmitter and possibly like a space network. So they may not send the information to one another until one gets close enough to Earth, to a relay station to send to the ground. This size, they may not have enough power to individually send to Earth. So it might end up being a space network. And I've been thinking about that a lot, that, hey, while it's out there, it can be the internet of space. So future exploration, hey, use this. We're just pinging the signal off of it. It'll route its way to Earth, with an IP number or whatever we, decide to use it. But we do want to look, I do still need a computing network innovations to make this happen. That's a component I'm still missing, so I'm still looking for partners in that area.
So you said you want to look at exoplanets.
Mm-hmm.
What type of resolution do you for?
I don't know the numbers, but from what Dr. Highland said, if we put them, he gave me a relative size, which would be, he said, if you put a telescope at each of A&M's campuses, that's roughly the size of Texas. That is the size you would need to see exoplanets. The other challenge is that because they're near a star, it's like looking at a firefly next to a spotlight. Okay, so that's the other challenge. That's kind of the techniques that are done is that the planets are passing in front of the star, and so they see the intensity of the star dip, and they say, oh, okay, there's a planet there. It dipped by so much, so this this large, and they can do a lot of mathematics on that. Maybe a few if they directly imaged it. He called me up maybe at the beginning of the year. So I said, I know it's still possible, Dr. Highland. We don't know yet how, but I think it's still possible. Then he called me up. He said, hey, Mike, I found a sensor that has the sensitivity that could most likely be, it has a sensitivity that will be needed to directly view exoplanets. The challenge is that the signal that you're trying to measure is smaller than the electrical noise within the electronics of the sensor. Okay, that's why it hasn't been done before. That's the main reason. He says now this sensor that they have, now it still takes a lot to get it to work. You have to use cryogenics to cool it. But he gave me an example. He said normal sensor, if the photon hits it, it may shoot out maybe 10 or so electrons. And this is just giving a relative example so I can understand it. It may say it shoots out 10 electrons. Once it hits the photosensor sensing device, 10 electrons shoot out, and those 10 electrons are measured, okay? And that's what you tell us, okay, we saw a photon. But unfortunately, the noise is hitting 10, but the noise is around 15 or 20. Just the background through the electrical wires, 15 or 20, you're not going to see it. Yeah, it takes a lot of them. He said this new one, instead of 10, it's 1,000 per photon hitting. 1,000 electrons come out. Noise is still 20, but now your signal is 1,000 per photon. He said now with that, he said Mike could get your exoplanet. Still some development work because it's new. It's sitting by itself. It's new. But he said now you've exceeded the signal noise level. Now you can do it. So you had another question about.
Yeah, you said you were looking for partners for the networking zone.
Yes.
Have you heard of the company Skybox?
Skybox. I think they're the crowdfunded. I think I have. Go ahead. Tell me about it.
They're using the same cube satellite design to put up commercialized satellites that view Earth so that consumers can get live satellite imaging of the Earth.
Okay.
Thought maybe that might be a partner to look into for the networking because obviously they're not to have a lot of the same networking.
Yeah, definitely. I'll keep that a note now because there are a lot of other CubeSat developers out there, and things are moving fast in the CubeSat world. So as we're speaking, new developments are coming about to make things better. But yes, Skybox, if they have an answer, we'd be interested.
Yeah, the Constellation, they don't have to have any kind of regular pattern. It's just the random noise maybe, or how?
Yeah, I'm going to leave that up to an expert in that area because I don't know what kind of pattern is needed. Like we're simulating a we're simulating this aperture. So do they need to all line up, or they need to be sprinkled around or a certain way? There should be some kind of efficient pattern because as they're moving around, they're filling all this space up. So if I only have maybe 10 of them, what's the best orientation to fill that space up the fastest and the most efficient way? So that's the question that we definitely need to answer on.
Because I was thinking that also because what happens when you have one that goes out on you and you're missing a piece of the pattern, you're missing part of the pattern, something like that. I mean, can you still, like within the software, correct for that and make it a workable image, or do you have to?
I think so. As long as you have two, that's the minimum, two, it will still work. But the clarity will go down. If you lose one, it will either take longer to produce an image or you'll lose the clarity or both. But you'll still get the full resolution. It's just you won't see as clear. But he said the more you have, the faster, the less time it takes to produce an image, and also the clarity increases.
What's your timeline? When you all open to money?
That's a good question. Right now we're all on volunteers right now, so volunteer time can be extended. Mean a long time. What I've told people is that we're working in phases, and going in that measure. I've said that, hey, if we had enough money, maybe 6 to 7 year time frame, but that's saying we have immediate sponsors and actual people to work on it full time. But on the volunteer level, we're here and there. Maybe A&M, I think he'll call me up and say, hey, we developed something new, or somebody else will tell me they've done something on their own. But it's kind of hard to gauge that on a volunteer time. I'll probably have a better answer later when we have more funds to get full-time people on it.
So if you is there color in this one, or is it just kind of black and white?
Yeah, great question. When it starts, it's only one wavelength of light. So you're combining, say, a shade of yellow, that's whatever that wavelength is of that particular shade. You're detecting just that. Okay, but you do your red, green, and blue, take it in yellow, or maybe a few of them in yellow, a few of them in red, so we'll have to test that out. But when it's actually done, it's only one wavelength, so it would be, for lack of a better term, black and white. You're just measuring intensity, a light and a low color. But when you combine the other shades, then you can combine those images and overlay them to make a color image. Because I do want to see a color image. I don't want to see black and white. I want to see color.
Skybox is working on. The way they're doing it, they're using low-grade photography and combining several images to do a single using a computer program.
Yes, and that technique I looked at early on as a good technique. To give an example, astronomers use it. They'll take one of these little USB cameras, put it in movie mode, and if you take a movie of the moon, you're getting so many frames per second. And then you combine that, and you have the clarity of I won't say the resolution, but you'll have extreme clarity because you have clouds passing over, you have distortions, but you overlay all those photos, and you will get a better clarity. So we'll do the same thing with this. Lots of photos, taking lots of data from different positions, and pretty much do the same thing.
How many students do you think are going to be working on this?
I hope a lot. I mean, I'm leaving up to the universities as we approach them. If they have particular subsystems that we're interested in, it depends on how many students are in their program. I've just sent Draper Labs has opened up an intern position for one student at their site that I've just sent a couple people off to. So there was one there. A&M has a few. So it all depends on who we're working with, kind of dictates that number. But yeah, hopefully we get, it's going to take a lot of people in a lot of various disciplines, even outside of technical discipline. I have a business background. I have a business base for this because this is a full system. So it's not just the science and engineering behind it. How do we finance it? How do we secure a facility? There's a lot of other avenues that we need other disciplines involved in it because it's going to be a full operational system.
Another question? All right, let's thank our speaker. A couple announcements. First off, next week we have Deborah Horwitz from LPI is going to be here talking about the moon and lunar landing sites that characterize the impact flux of the ancient solar system. Also, as I mentioned before, we have 3 weeks from today is the student presentation. So the students in the class, I'd like you, I'm going to send out an email as well, but email me the title you want for your talk. The way we're going to arrange it is grad students, you're going to have up to 20 minutes, that's 15 minutes for your talk, 5 minutes for questions, target. Undergrad, it's going to be a little shorter, it's going to be 15 minutes total, 12 minutes for your talk, 3 minutes for questions. And if you have any questions about what the talks are going to entail or anything like that, you can email me, but what I'm planning on doing is on April 17th, after the last regular speaker, I'm going to go through more direct information about what to expect in the talk. And so we've got basically, over the next week, I'd like to get the information you guys on the titles. By the 17th, I want to be able to present you guys a list of, when you're going to be talking, even though I expect everybody to stay here for all of the talk, no leaving early. And after the 24th, then if undergraduates are done and grad students are going to have a couple weeks to get your papers in. So with that, thank you.